Hello class. So today we're going to be reviewing the different gas laws, and we're going to be exploring what happens when we have a situation in which there is a change in multiple variables, right? Because oftentimes we're not just going to have a change in volume or a change in temperature or a change in pressure. A lot of the times we're going to have a change in temperature and pressure, and then we have to figure out, okay, well, how does that impact our volume, for example? And we call that the combined gas law. But before we get into that, let's just quickly review the different relationships we've explored so far. So first up is Boyle's law, and Boyle's law, we explored the relationship between pressure and volume. What was that relationship? What was that relationship? Well, it was inverse, right? Our pressure and our volume were inversely proportional. What does that mean? Well, if they are inversely proportional, that means that if our pressure goes up, our volume goes down. And let's say if our volume goes up, our pressure goes down, and vice versa, right? So they have equal but opposite changes. Now if we look at our next law, which was Charles' law, we explored the relationship between volume and temperature. What was that relationship? Yeah, that's right, they were directly proportional. So if we increase temperature, we increase volume. If we decrease volume, we decrease temperature. And then last up was the Gay-Lussac's law. Now, this was the law in which we explored the relationship between pressure and temperature. How were those two things related? Yeah, that's right. It was directly proportional. So our pressure is directly proportional to our temperature. Now, in solving these problems, I gave you a basic overview of what to do, right? I said you need to predict, and then you need to multiply by the ratio, which fits your prediction. We are still going to be using that same set of steps, except now we are going to be making two predictions when dealing with the combined gas law. But again, before we get there, I want to quickly show you the equations that apply to each one of these laws. I haven't showed you these equations up to this point because I wanted you to think about these numbers in ratios. I wanted you to predict. I wanted you to work on the skills that are needed for stoichiometry. But if you are one of those formulaic thinkers, here are the equations. So if you've really been struggling, maybe these equations will work better for you. For Boyle's law, it is P1V1 is equal to P2V2, right? You would plug in for the variables you know and solve for x. For Charles' law, it is V1 over T1 is equal to V2 over T2. Again, you'd plug in for what you know, solve for x. And for Gay-Lussac's law, it is P1 over T1 is equal to P2 over T2. So those are the equations that you could utilize in order to solve for these. And lastly is the combined gas law equation. And the combined gas law equation will be P1V1 over T1 is equal to P2V2 over T2. Now, I will recommend, again, that you solve these equations with the strategy that I've shown you, because that will help you in stoichiometry. Even with combined gas law, we can predict and we can multiply by the ratios we need in order to solve those problems. So let's do a couple example problems. Okay, so if a balloon rises into the atmosphere to an altitude of 3,000 meters, the balloon was filled to a volume of 2.0 liters on a warm sunny day when the temperature was 27 degrees Celsius and the pressure was 101.3 kilopascals. What is the volume of the balloon at 3,000 meters if the temperature is negative 8 degrees Celsius and the pressure is 70 kilopascals? So again, we're going back to the weather balloon example because it's a great example of the combined gas law. So when we're looking at these changes, the changes in pressure, the changes in temperature, we're going to treat these as independent of one another. And I'll show you what I mean when we do our predictions. So first off, let's write down what we know. So initially, when the balloon was filled, what were the conditions? So we know initially that the volume that it was filled to is 2.0 liters. We know that the pressure when it was filled was 101.3 kilopascals, aka 1 atmosphere of pressure. And we also know that the temperature was 27 degrees Celsius. However, you should know already that that's not going to cut it, degrees Celsius. What do we need to convert that into? Yeah, that's right, we have to convert that into Kelvin. How we do that? We must add 273.15, which gives us 300.15 Kelvin. On the flip side, we are looking for our final volume. We know the pressure at 3,000 meters is 70 kilopascals. And we know that the temperature at this altitude is negative 8 degrees Celsius. And again, we should convert this into Kelvin, which gives us 265.15 Kelvin. Okay, so that's everything we know. Now let's predict how our volume is going to change as a result of these changes in our temperature and our pressure. Let's look at pressure first. So pressure went down, right? It went from 101.3 kilopascals to 70 kilopascals. As a result, what is going to happen to our volume? Think back to Boyle's law, right? Pressure and volume are inversely proportional. So a decrease in our pressure is going to cause, therefore, an increase in our volume. And if we look at our temperature went down. What is the relationship between volume and temperature? Think back to Charles' law, right? They are directly proportional. So a decrease in temperature will therefore result in a decrease in our volume. So a decrease in temperature will therefore result in a decrease in our volume. Now, when we were solving these problems previously, we multiplied by the ratio, right? The ratio of our temperatures that would cause the change in our volume. The ratio of our pressures that would cause the change in our volume. We are going to do the exact same thing. So, we know that we have 2 liters of gas. Now, what is the ratio of my pressures that will cause my volume to go up? Am I going to do 101.3 over 70, or am I going to do 70 over 101.3? Yeah, that's right. You want to have the larger number as your numerator, so it's going to be 101.3 kilopascals over 70. And then we're going to multiply this by the ratio of our temperatures. Now, a decrease in temperature therefore results in a decrease in volume. So what am I going to multiply by? Am I going to multiply by 300 over 265 or 265 over 300? Well, we want it to go down, so our larger number should be in the denominator. So we're going to do 265 over 300.15. And if we do the math, this gives us 2.56 liters. So the new volume of our balloon as it rose to a height of 3,000 meters is 2.56 liters. Okay, so let's do another example. A gas has a volume of 125 liters at 325 kilopascals and 58 degrees Celsius. Calculate the temperature in degrees Celsius to produce a volume of 22.4 liters at 101.3 kilopascals. So again, let's start off by writing down what we know. We know that our initial volume is 125 liters. We know that our initial pressure is 325 kilopascals. And we know that our initial temperature is 58 degrees Celsius. Let's take a second now and convert this to Kelvin. So we're going to add 273.15 to give us 331.15 Kelvin. All right, so what are the final conditions of our gas? Well, the volume changes to 22.4 liters, and the pressure changes to 101.3 kilopascals. And what is the question asking us for? It's saying as a result of this change in volume and this change in pressure, what is our new temperature? So in order to figure that out, we again need to predict. So what happened to our volume? Our volume decreased. Therefore, what is going to happen to our temperature? Well, they are directly proportional. So our temperature will also decrease. And what happened to our pressure? Well, our pressure went down. And how is pressure and temperature related? Well, they are directly proportional. So if our pressure goes down, our temperature must also go down. Now, we are going to expect our temperature to decrease by a lot here, right? What is the reduction we see in our volume? Well, that's effectively a 5-factor reduction. What about pressure? Well, that's over a 3-factor reduction. So we would expect, at a minimum, our temperature should be about 8 times smaller, at a minimum. If you do not get a number that small, you know you did something wrong. Okay, so now let's do step 2. Let's multiply by those ratios to get our final answer, to see the result on our temperature. So what is our temperature initially? It's 331.15 Kelvin. And now let's multiply by the change in our volume. Well, our volume went down, and therefore our temperature should go down. So how do we decrease our temperature? We are going to multiply by 22.4 liters over 125 liters. What happened to our pressure? Our pressure also went down. So what are we going to multiply by? We will multiply by 101.3 kilopascals over 325. Again, if you want your numbers to decrease, put the larger number as your denominator. Now, what does this give us? This gives us 18.50 Kelvin. Are we done? No, right? The question is asking us for degrees Celsius. So we must subtract 273.15 in order to get our answer in degrees Celsius. And that number is going to be negative 254.65 degrees Celsius. Super, super, super cold, and that's what we expected. Okay, so now we're going to explore what happens when we throw moles into the mix. I know you thought you were done with stoich, but stoich only works with gas conversions at STP. So let's quickly explore one of those conversions, something that you would have done previously. So let's say, for example, you have 4.2 grams of hydrogen gas. And I asked you, how many liters of hydrogen gas is this? Well, if you look at your conversion charts, you'll see that, well, first we need to convert this into moles, and then we can convert this into liters. So how do we convert this into moles? Well, we need to divide this by the molar mass. What is the molar mass of hydrogen? The molar mass of hydrogen gas is, for every 1 mole, there is 2.02 grams. And let's explore now, well, how do we convert from moles to liters? And what did you learn in stoich? Well, you learned that the conversion is for every 1 mole, there is 22.4 liters of gas. And if you do the math here, you'll find that 4.2 grams of hydrogen is equal to 46.57 liters. Now, there's a stipulation here. When is this only true? When is this only true? Well, this is only true at standard temperature and pressure, right? This conversion factor here, this is only true at STP, right? This is only true at STP. And what is standard temperature and pressure? Well, that is going to be 0 degrees Celsius at 1 atmosphere of pressure. What happens, though, if we have a gas that is not at STP? Well, if it's not at STP, we are going to have to convert it to STP conditions in order to do stoichiometric problems, right? Because the only conversion we have between moles and liters of gas is 22.4 liters. So with any mole-based gas problem, you have to constantly be asking yourself, is this at STP? Is this at STP? If it is not at STP, you cannot do this conversion. So let's explore now a couple example problems that will help accentuate this fact. Okay, so a balloon is filled with 4.2 grams of hydrogen at standard temperature and pressure. The balloon is released and rises to a height of 2,000 meters. At 2,000 meters, the temperature is negative 20 degrees Celsius and the pressure is 600 millimeters of mercury. What is the volume of the balloon at 2,000 meters? Now, a lot of students will be tempted to simply just convert 4.2 grams to moles and then moles to liters at STP and then say that's our volume, that's the volume of our balloon. But that's not the case, because what is happening to our balloon? Well, the temperature is changing and the pressure is also changing from STP. So let's write down what we know. What do we know? Well, we know initially what is the temperature that our balloon is experiencing. Remember, it was filled at STP. So at STP, what is our temperature? Well, it's 0 degrees Celsius. And let's save ourselves a little bit of heartache right now. Let's convert this into Kelvin. So that's going to be 273.15 Kelvin. And we also know at STP, what is our pressure? Our pressure is 1 atmosphere. Now, what is that in millimeters of mercury? That's 760. So this is 760 millimeters of mercury. And then lastly, what is our volume? Well, we're going to have to do a little bit of math for that one. Luckily, we've already done it, right? Think back to the example problem I just showed you. I already solved what the liters of gas would be at STP. But we'll leave that blank for now. So, what is our final conditions? Well, our final temperature is going to be negative 20 degrees Celsius. And if we convert that to Kelvin, we get 253.15 Kelvin. And we know that our final pressure is going to be 600 millimeters of mercury at 2,000 meters. Now, what is this question asking us for? Well, it's saying, what is our volume? At that height, what is our volume? In order to figure that out, we need to know what our volume was at STP. How do I figure that out? Well, we are going to do the exact same thing I just showed you. So we have 4.2 grams of hydrogen gas. And we are going to divide that by our molar mass. And we are then going to multiply this by 22.4 liters per 1 mole, right? The number of liters per mole at STP. And this gives us a volume of 46.57. So we have now our initial volume. So now we can figure out, well, what was our final volume? When we changed the pressure and we changed the temperature, what happened to our volume as a result? So what are our predictions going to be? Well, our temperature went down. Temperature and volume are directly proportional. So if our temperature goes down, our volume must also therefore go down as well. Now, what about our pressure? Our pressure decreased as well. But is pressure and volume directly proportional or inversely proportional? Yeah, that's right. They're inversely proportional. So when our pressure goes down, that means that our volume, as a result, will go up. So we have our predictions. So now all we need to do is we need to multiply our volume here by our ratios that fit our predictions. So if we have 46.57 liters, let's multiply this by the ratio of our temperatures that will cause our volume to decrease. So we'll put the larger number as the denominator. That's 253.15 Kelvin over 273.15 Kelvin. And let's multiply by the ratio of our pressures. That will give us a higher volume. So that is going to be 760 millimeters of mercury over 600 millimeters of mercury. And this gives us 54.67 liters. So it's super important when you're solving these problems to ask yourself, is my gas at STP? Is it not at STP? And if it is at STP, you know that's your initial conditions, right? That's your initial temperature, that is your initial pressure. Sometimes I may ask you to go in the reverse direction, right? And that will be the next example we do. Okay, so a balloon is filled with 4.2 grams of hydrogen gas. What is the volume of the balloon at 50 degrees Celsius and 2 atmospheres of pressure? A seemingly simple question, but it is in fact quite challenging because are these conditions at STP? No, of course not. So how can I possibly figure out the volume at these conditions? Well, first, we have to find the volume at STP, right? That is the only way we can go from moles to liters. So we've already established, well, at STP, what is our pressure? Well, it's going to be 1 atmosphere. What is our temperature? Well, it's going to be 0 degrees Celsius, or that's equal to 273.15 Kelvin. And what is our volume? This is the same volume you calculated previously. So that is going to be 4.2 grams of H2. And we're going to divide this by our molar mass. For every mole, there is 2.02 grams. And then we are going to multiply this by 22.4. Because there is 22.4 moles per liter at STP. And remember, at STP, this will give us a volume of 46.57 liters. So we know initially what our pressure, temperature, and volume are, right? We don't say it in the question, but we don't need to. You need to assume STP conditions and figure out the volume at those conditions, and then use combined gas law in order to figure out the final conditions, right? What is the change in our volume as a result of the change in our pressure and the change in our temperature? Speaking of which, what is the change in our pressure? Well, it is going from 1 atmosphere to 2 atmospheres of pressure. And our temperature is going from 0 degrees Celsius to 50 degrees Celsius, which, when we convert to Kelvin, is going to be, that's going to be 323.15 Kelvin. And what are we looking for? Well, we're looking for what is the volume at these conditions, right? What is the volume at this pressure and this temperature? So now it's just a question of, well, as a result of our change in pressure, what happened to our temperature? To our volume. Well, we increased our pressure. So if we increase our pressure, what therefore is going to happen to our volume? Well, it's going to go down, right? It's going to go down because they are inversely proportional. What happened to our temperature? Our temperature went from 273 to 323. It went up. And temperature and volume are directly proportional. So by increasing our temperature, therefore we will increase our volume. So now we need to multiply by our ratios in order to get our final volume. So 46.57 liters. What was the change in our pressure? Well, it increased, therefore we get a decrease in our volume. So what ratio am I going to multiply by? I'm going to multiply by 1/2. And since our temperature went up, therefore our volume should go up, I'm going to multiply by 323.15 over 273.15. And as a result, our final answer is 27.55 liters. So at this temperature and this pressure, our volume of 4.2 grams of hydrogen gas will be 27.55 liters.